So let us start. In this lecture, we will consider thermodynamics of rarefied quantum gas. Rarefied means that the gas has low density and low concentration of particles. In the previous lecture, we have obtained the grand thermodynamic expansion for the quantum gas consisting of identical particles. We get something like this. Here, G sub S is spin degeneracy, is the number of spin states. Here, S is a particle spin. And here, we have integral over the dimensionless variable x. Here we have two signs. The upper sign, okay, let me take whiteboard marker of another color, corresponds to bosons, and lower sign corresponds to fermions. We also found a classical limit for this grand thermodynamic expansion, for grand thermodynamic potential. So we assumed that the chemical potential is the ratio of chemical potential to the temperature is a big negative number. So this exponent is much less than 1. In this case, this exponent is much bigger than unit, and we can omit these contributions, and we can forget about statistics. And we find the classical expression for grand thermodynamic potential. Okay. Our problem was the following. The grand thermodynamic potential depends on the chemical potential mu, which is not convenient variable. We prefer to use the particle number n instead, because particle number has a clear physical meaning, while the chemical potential is a useful variable, but it's not so convenient in studies of gases. It's very convenient when we consider chemical reactions and so on. If the number of if the amount of substance n is constant, and is preferred variable. So to study, so if we, so okay. So to study the properties of quantum gas, it's better to use not the ground thermodynamic potential, but another potential that depends on the particle number. So the natural variables for ground thermodynamic potential are temperature, volume, and chemical potential. We dislike this variable. We want to use another thermodynamic potential that depends on the temperature instead, on the particle number instead. This is a free energy. And we want to compute free energy, which equals to the ground thermodynamic potential, theta V mu. We are making a Legendre transformation plus mu n. And here we have to express mu in terms of temperature, volume, and particle number. This equation is defined, this dependence is defined from the condition n equals to the partial derivative ground thermodynamic potential with respect to mu for constant theta and v. The computation of, when we work in the most general case, the computation of free energy is as difficult. The work with the free energy is as difficult as the work with ground thermodynamic potential, because the relationship between the total number of particles and chemical potential is very difficult. However, we can simplify the problem by assuming that the gas is rarefied. So the density of gas is low, and this condition is satisfied. But now we consider not only the leading term, but also the first quantum correction to the classical thermodynamic, classical ground thermodynamic potential. And approximate computation of free energy, as we will see, is quite simple, and we can find the free energy of the quantum gas up to first order correction in maybe I can say that in density. In fact, this expression is connected to density of the gas. And I will start from certain statement which can be proved in very general setting, but I need its particular case. Let us write corollary. And we can, and we will give the name, its particular case, of theorem on small corrections. Okay. And now I'm going to formulate and prove the statement. Suppose that the ground thermodynamic expanded potential of the quantum gas is given by a sum of classical ground thermodynamic potential and a quantum correction. We think that the quantum correction is small. By saying small, I mean that we have a certain parameter. We have a certain parameter. When this parameter tends to 0, tends to certain number, this correction tends to 0. In our case, this parameter is the exponent of chemical potential divided to the temperature. When this parameter tends to 0, we expect to obtain the classical ground thermodynamic potential from this omega. Then the free energy of the system can become the free energy up to first order in this small parameter can be computed as follows: F equals omega of theta V mu. And here I take the classical value of mu. And mu classical depends on theta V n. Okay, it's too complicated. Okay, mu classical plus mu classical multiplied by n. Here, mu classical is a classical value of chemical potential. It's determined by condition n equals to the minus partial derivative of classical ground thermodynamic potential with respect to mu, and then we put mu equals to the mu classical. This is not precise expression for free energy. This expression just reproduces first and second, just reproduces classical contribution and first order correction. If we want to compute the exact value of FF, have some high order corrections which become small, which can be ignored if omega is small. Okay, let us prove this statement. Okay. Proof. Suppose, okay, no, not true. Okay. Okay. As far as correction to the ground thermodynamic potential is small, we can expect that the exact expression for chemical potential is given by the classical contribution, which is determined by this equation, and plus some correction delta mu. If the correction in thermodynamic potential is small, we may expect that this delta mu is small. Now, let us use the general definition for free energy, and with a count of this decomposition for mu. So we have F equals to omega of theta V mu classical plus delta mu plus, and here I write mu classical plus delta mu multiplied by n. Now we see that omega depends on this sum, and delta mu is small. So we can expand grand thermodynamic potential in small parameter delta mu. I will expand it up to the first order. I'm not interested in the second order corrections because I believe that this expression is correct only up to the first order. So I have omega theta V mu classical plus a derivative of grand thermodynamic potential with respect to mu for mu equals to mu classical. Okay, mu equals to mu classical multiplied by delta mu plus mu classical plus delta mu multiplied by n. Now, I'm interested in this term. Delta mu is a small number. So, without loss of precision, I can replace this grand thermodynamic potential by its classical value. This is the first order correction, and this difference between omega and omega classical is of first order too. So the product of this difference is a second order correction, which is not interesting for me. Now, I look at the definition of classical value of mu classical. So I see that this term is exactly minus n. So I suggest you to rewrite, but I prefer to erase. And here dot. Now I see that two terms annihilate each other. And now, I got what I want. Plus classical multiplied by n. Please note that this representation is true only up to first order corrections in delta omega. So it's approximate formula. We proved the statement, okay. And now let us write a simple remark. Okay, I do not want to write very loud, so I erase here, and you can write something below. As we see, omega is given by the sum of classical expression plus delta omega. So when we substitute the classical value of thermodynamic of chemical potential, I will get something like this. Omega classical or theta v mu classical and plus correction delta omega of theta v mu classical. Now we can rewrite the free energy as follows. The classical part plus correction theta v mu classical plus this term. Here we have some kind of magic. Look, these two guys give a classical value of grand thermodynamic of free energy. So I can write F classical, and it is expressed in nature variables plus small correction so if we want to compute the free energy of gas, of rarefied quantum gas, we should just find the first of, we could find the first order correction and express it just in terms of classical chemical potential, classical chemical potential, volume temperature. Just substitute mu classical and forget that this correction comes from the grand thermodynamic potential. In other words, if we say that this is correction, if we say that this is correction to the free energy, we can say that delta F expressed terms theta Vn is just delta omega as theta V mu classical, which depends on theta V and N. Okay, so we have a receipt of computation of free energy of the system. Let us proceed with these computations. Okay. Take another whiteboard. Let us first find. Oh, no. It's not too hot. Okay.
Дмитрий Сергеевич, а можете, пожалуйста, чуть доску верхнюю опустить?
Вот это?
Да, спасибо.
Окей. Спасибо вам. Okay. Okay. So let us proceed with computations. Okay. Okay, I prefer to write here. No, it's better to use the whiteboard. Here we have the expression for ground thermodynamic potential. And we are going to find the first order correction to the potential, the first order quantum correction to this potential. Okay, it's classical, it's not so good place, so I will erase, and erase. And we are looking the limit exponent of mu divided by theta is much less than 1. So mu appears only in one place, in the exponent, in the integral. So I suggest to transform this function that stays under integral into the more convenient form. So let me write. I forgot about integral and the x, and to transform only this part. Okay. And now I know that the exponent is very big number. It's very big. Because exponent of mu divided by theta is small. So exponent, okay, so why it's big number? Because it's e of x. Okay, because okay. So it's very big positive number and x is positive. So exponent in big positive number is very big number. So I multiply, so I divide both the up and down parts of the fraction by this exponent. So I have exponent of mu divided by theta minus x to the power 3/2. And here I get 1 minus plus x mu divided by theta minus x. Now this contribution is much less than 1. Because exponent of mu divided by theta is small, is a big negative number, and minus x, we get even bigger negative number. And here I make approximation. Here I make approximation. I use the decomposition of a fraction. So 1, I use the formula 1 minus plus z equals to 1 plus minus z plus z squared, and etc. I'm interested only in the first order correction. So I forgot anything else. And z, this, and here z should be a small number. Okay, and here this exponent serves as z. So I get exponent of mu divided by theta minus x. This one, this is here this exponent, and now I write the fraction 1 plus minus exponent of mu divided by theta minus x to the power 3/2. I can transform, I can rewrite this expression in many. Okay, I will not proceed with the information right now. It's sufficient. Now I substitute the approximate expression for integrals. This one, okay, this one here into the integral. To simplify expression, I open this bracket, I transform it into the sum, and then collect, and in this case, I replace this integral by sum of two integrals. So I get the following: omega equals to 1/3 gs for p 2m theta to the power 3/2 theta v divided 2e h bar to the 3rd power. And here I write very big bracket. And so what I do? Exponent of sum is a product of exponent. So I use the idea that the exponent over mu divided by theta minus x is just exponent of mu divided by theta multiplied by exponent of minus x. An exponent of mu divided by theta is a constant. It does not depend on x, so it goes out of integral. Okay, I have not sufficient place, so I write very big bracket here. Exponent of mu divided by theta integral exponent of minus x to the power 3/2 dx. And this is a classical contribution. Now we have a first order correction. I will have plus minus. Please look that we have two exponents, so we have e to the 2nd to the power 2 multiplied by mu divided by theta, and here minus 2x. So and here exponent minus 2x to the powers x to the 3/2 dx. And this is the first order correction. There should be higher order corrections, but I forgot about them. Now, these integrals can be computed. We have computed the first integral on the previous lecture. So I just write down the result. It's 3 over p multiplied by square of pi. Now we can easily find the other integral. Minus 2x multiplied to the x to the power 3/2 dx. And here we make a variable change. We put x equal to the u divided by 2. And dx equals to du divided by 2. So we get from here 1 over 2 square of 2 and 1/2 from the x. So we get a common factor, 1 over 4 multiplied by square of 2. And here we get the same integral as in the previous case. Minus u x to the u to the power 3/2 du. And we can easily compute this integral, and we have 3 over 16 square of 2, okay, 3 square of 2 multiplied by pi divided by square of pi divided by 2. Square root of pi divided by 2. Okay. And now we can write down the expression for the ground thermodynamic potential up to first order corrections up to the first order corrections. Okay. I want to see this formula, so I use the whiteboard in this way. Okay, and as far as I know, this is a 3 over 1/2 square of pi. I just collect all the classical. I just collect all I have into the classical ground thermodynamic potential. I want to make a classical ground thermodynamic potential as a common multiplier, and then write something as a correction. So I'm transforming into steps. So I write 1/2, 1/3 g as 4 pi 2m theta to the 3/2 theta v 2 pi h power to the cube. And here I have 3 over 4 square of pi, square root of pi. Here 3 over 4 square root of pi. And I may multiply it by this exponent. Mu over. And I take this as a common factor. And I get here this 1 plus minus. Here 4 over 1/2. Here 1 exponent, extra exponent. 1 4 over 1/2 e power mu divided by theta. I can simplify this expression. So I erase here, erase here.
Извините, пожалуйста, вы не могли бы чуть-чуть опустить доску вниз?
Oh no, sorry.
Все, вот спасибо большое.
Sorry. Okay. So and then I collect pi. So got pi 2m pi 2 pi m theta to the 3/2. In fact, this is classical ground thermodynamic potential. So we can write omega equals to the omega classical multiplied by 1 plus minus 1 over half square root of 2 multiplied by exponent of mu divided by theta. Okay. And here we see that we have a classical part. And here we have first order correction. This is a form of thermodynamic potential we seek for. Now we are going to find free energy. Okay, it's okay. Now we are going to find free energy. At first, we have to determine the classical value of chemical potential. Let us compute the derivative of classical thermodynamic potential with respect to mu. Okay, the classical thermodynamic potential is this one. When we differentiate by mu, we had to use differentiation rule for the composition. When the derivative by its exponent, we get exponent, and when we take derivative of mu, of argument of exponent, we get 1 over theta. It kills 1 theta. So I get something like this: GS 2 pi m theta to the power 3/2 V divided by 2 pi h bar to the power exponent over to find the classical value of chemical potential. I estimate this expression for mu equals mu classical, and here I put mu classical. Okay, I this here put minus, here plus, and put it equals to n. When I get this equation, I just say that we have classical gas. So the thermodynamic potential is equals to the thermodynamic potential of classical gas. And then use the relation between the number of particles and derivative on grand thermodynamic potential. Okay, and I get this equation. Now I have to express mu from here. It's not difficult. At first, I express the exponent, and it's very convenient for me. E exponent of mu classical divided by theta equals to what? Equals to what? Okay. GS 2 pi h bar q multiplied by n and divided by GS 2 pi m theta 3/2 V volume. And for chemical potential, for the classical chemical potential, we get this equals to the theta logarithm of this expression, of this expression. Okay. Before we proceed, I want to address a question about the physical meaning of the condition. Yeah, exponent over mu divided by theta much less than 1. Okay. As we assume that the gas is rarefied, the chemical potential of the gas is close to the classical chemical potential. So I can write here mu classical. And we know the expression for this exponent now. And this expression should be much less than 1. And now we are trying to understand what does mean the condition. Does this mean condition which is supposed to be true for a rarefied quantum gas? Let us consider at first, let's consider several parts. At first, let us look this contribution. It's the phase space volume, for a single quantum state. Here volume, and here 2 pi m theta. If we forgot about pi, 2 m theta is a let's say average value of particle momentum. And when we do p m theta to the power 1/2 is the value of momentum. So this to the power 1 with 3/2, it's like p cube. Okay, it's bad. I have no marker. Now I have a good marker. So it's p cube. So p cube v is and now p cube for the average particle energy, let's say. Then p cube multiplied by v is a phase space volume. Phase space volume that contains all the particle states that are admissible. The states with high value of momentum are not admissible because the energy of the particle is not sufficient. The fraction g sub s, that multiplier g sub s, just accounts that the particle has 2s plus 1 spin states. So if n is ignored, here we have a ratio of volume of a unit phase space state, and the volume of a space that is admissible to the system at the current level of temperature. Dividing 1 over this, we get here, when we divide here, we get the number of quantum states. That are admissible for the system at this temperature. And we take into account n. So we divide the particle number for the number of quantum states. Once this fraction is much less than 1, this means that the average number of particles in quantum state is much less than 1. That is, the occupation numbers are small. This is a correct interpretation because we know that the statistics of Fermi and Bose transform into the Boltzmann-Maxwell statistics for small occupation numbers. Now we proceed with the computation of free energy. I'm using a formula F equals to omega of theta V mu classical plus mu classical multiplied by n. I like this formula bigger than, I think this formula is most convenient in this case. So I'm making a substitution. Okay, I'm writing omega classical at first. Okay, omega classical, it's 2 pi m theta to the power 3/2 gs theta v divided to t pi m to t pi h bar to the cube, to the third power. And now I know, okay, let me omega classical recall. What is omega classical? Minus gs 2 pi m theta such half 3/2 theta v 2 pi h bar to the third power exponent mu divided by theta. So I rewrite the prefactor at the exponent, and now I say I'm substituting exponent. Okay, I see exponent here. So I'm writing 2 pi h bar multiplied by n divided by gs 2 pi m theta to the power 3/2 v. And now I open this bracket. 1 plus minus 1 over 4 multiplied by square root of 2. And here exponent And I should, and now I reproduced ground thermodynamic potential, and I need the term that contains N. So it's continuation of the formula. I'm looking here, new classical, theta, N, it's N from here, and then logarithm. Okay. Now I can make several simplifications. At first, almost everything here was annihilates. Almost all contributions here annihilate each other. Here, GS to PH cube, V, this bracket, and only N and theta survive. Epsilon minus. So I prefer to, and here I have theta N. So I prefer to take the numbers theta N as a common factor, minus theta N. When I take minus here, I should interchange the fraction in logarithm. Значит, okay, and now, and I prefer to open the brackets and logarithm just for simplification. So theta N, so I have 3 half logarithm theta plus logarithm V divided by N. It comes from here. And here I write plus logarithm of what of 2 pi m to the power 3/2 gs 2 pi h bar. And now I have from here, I should have -1. -1 here, it's just exponent in logarithm. It's a free contribution into the free energy of classical gas. Now I have to identify the first correction. So here minus, and here minus plus minus, so I have minus plus, and now I rewrite here n theta 4/2 over square of 2 pi h bar and gs pi m theta to the power 3/2 divided by v, and this is all. I denote the classical part as F classical. I will get that F equals to the classical value of ground thermodynamic potential minus plus n theta 4/2 2 pi h bar pi m theta gs to the power 3/2 v. When we look at this expression, it's look like some kind of decomposition of classical free energy in the powers of particle concentrations. Okay, it can be understood in such a way, because the small parameter is in fact proportional to the concentration of particle. So, okay, let us now we can study a thermodynamics of rarefied quantum gas. We can compute various thermodynamic functions, and we start from what's the first? And I think it's better to start from pressure. Pressure is determined as a derivative of the free energy with respect to volume minus derivative of free energy for constant temperature and particle number. And we know the pressure of ideal gas it follows from Mendeleev-Clapeyron equation. And now we are going to find the first order correction. So here only here, when we differentiate, we get v squared minus v squared. As we have minus, the sign will not change, and instead n over v, we get n squared over v squared. Minus plus theta over p over square of 2, no, 1 over 4 multiplied by square of 2, h cubed gs 2 pi m theta to the power 3/2. And here we'll have an n squared v squared. If we consider the classical pressure of classical gas as a common factor, we can write P equals to the P classical minus plus, and theta here, theta n, 1 over half over 4 multiplied by square of 2, pi h bar, gs 2 pi m theta to the power 3/2 n divided by v. It's some kind of virial expansion. So we have a leading term in concentration here, and this is the first order correction. It's very important that the sign of the pressure correction depends on the statistics of particle. It is clear that in the whole of range of temperatures, the pressure of classical gas is lower than the pressure of fermions and higher than the pressure of bosons. In the other words, the pressure of rarefied boson gas always lower than the pressure of classical gas. The pressure of rarefied Fermi gas is higher than pressure of classical gas. Now we can make a similar analysis with the entropy. It's a minus partial derivative of free energy with respect to the temperature. I do not want to differentiate classical part of free energy. It's not interesting for me, so I write the entropy of classical gas. And now I take a derivative with respect to temperature. Please note that we have temperature here and temperature to the 3½ power here. So if so the total degree of temperature is 1 minus over half. When I differentiate, I get to the temperature to the power minus 3½ I get minus, but this it annihilates with this minus, and I get 1/2 here. So I have minus plus 1/8 square of 2. Here n. I have no theta because I differentiate by theta, and here 2ph bar and gs 2 pi m theta to the power 3/2. For classical entropy, only temperature dependence for me is interesting. So when I differentiate here by temperature here, I get n multiplied as 3/2 logarithm theta.
Дмитрий Сергеевич, можно спросить?
Okay.
А вот там в выражении для свободной энергии, вот откуда она, вот там n на тета разделить на 4 корня из 2? А откуда взялась вот эта n на тета, если мы ее за скобки выносили? Она не должна быть в знаменателе тогда? Потому что ее изначально там не было, ее, наверное, знаменательно.
Okay. Okay. The question why we get n multiplied by theta here? Let us look thoroughly to this expression for the free energy. Okay.
Можете чуть-чуть доску опустить, пожалуйста?
Okay. So here almost all contributions annihilate except minus n theta. We must have n here because the free energy is an extensive function. So it has to increase with the growth of the system number. Please note, this contribution is dimensionless. It is extensive because here n and here v. So we must have n here. We get theta because of dimension. Please look, F has the dimension of energy. So we had to have a contribution with the dimension of energy. The correction to the free energy appears here when we multiply n theta by the correction to the grand thermodynamic potential. And these two guys give here. Please note, that F classical is not a common factor. Here I use additive form of thermodynamic potential. The leading term is the classical value of F, and this addition is the first order correction. Is it okay?
Ну, вы там, наверное, потому что скобки нет еще одной, я поэтому запутался.
Okay.
Ну, ладно, спасибо.
You're welcome. So, when I look at the classical entropy theory, I'm interested only in the temperature dependence. And 3/2 logarithm theta plus something that doesn't depend on temperature. You can compute yourself. Okay, as we see, the entropy of classical, I mean Boltzmann gas, is always higher for the fermions, and always we see that fermions have higher entropy than classical gas, and bosons have lower temperature, of course, than the classical gas. Now we can compute the heat capacity. As usual, we use the standard formula. And again, we have a classical heat capacity plus some corrections. And it's important that the temperature here is in negative power. When we will differentiate, we change the sign here. So we get 1 minus after differentiation. So we will have not minus plus, but plus minus. Differentiate 3/2. So we have 3/16 square root of 2. And 2 pi h cubed and divided gs 2p m theta, so 3/2 v. And we know what is a classical heat capacity. It's a 3/2 multiplied by n. So I can write 3/2 n, and it's not a good idea. So classical heat capacity, we can compute it by this formula. It's 3/2 n. And it's convenient to take this factor as a common number. So I have CV classical multiplied by 1 plus minus 1/8 square root of 2, 2 pi h to the cube, and divided by gs 2p m theta to the power 3/2 v. Okay. We see that we have a correction to the temperature. So the first important conclusion that CV, the heat capacity, is a function of temperature. It's not a constant in the quantum case. The second conclusion is that the classical value of heat capacity is lower than the heat capacity of bosons and higher than heat capacity. not a good idea. CV here. CV classical. So if I write down a plot of heat capacity of quantum gas, I will get something like this. Here, temperature. Here, heat capacity. Okay, I write small heat capacities. It means for one particle. And here I have the classical value of CV classical. The classical value of heat capacity, it's 3½ For bosons, the heat capacity tends to 3½ from higher values. For fermions, it tends to 3½ from lower values. Please note that I do not continue these curves to the area of lower temperatures, because at the lower temperatures, the quantum effects can be very important. So we will consider later. And here I write bosons, and here I write fermions. It's interesting to compute the internal energy of the quantum gas. Now, here I prefer to use the equation, the formula of Gibbs-Helmholtz. d by d theta of F divided by theta for constant n and v. This formula needs to be proved. Let me demonstrate that it's true. Let me compute this combination. Here I need to compute the product of fraction functions. So I use Leibniz rule. When the derivative bites by theta, I get minus theta squared, and here theta squared minus theta squared, so I get f. When the derivative bites theta, I get f minus, f minus theta, here theta squared and theta give theta, minus df d theta for constant n. But this is an entropy, minus entropy, so get f plus theta s, get u. Okay, the formula is proved. And now I'm going to compute this. It's not good that I forgot. Okay, I'm going to compute this derivative. When it's clear that when I substitute f as a sum of classical f and correction, the classical f will give me a classical internal energy of the gas, which is known. And here I have correction. So I have to divide by theta and differentiate. So when I divide by theta, I have theta to this power 3½ So here will be 3/2 to the power 3/2. When I differentiate, I get minus 3/2. So 8 divided by 8 multiplied by square root of 2 and theta. I don't know the correct sign. I will determine slightly bit later. 2ph bar multiplied by q v divided by gs 2p and theta to the power 3/2 and v. Here n. Okay, let us determine the sign. Here I have minus. Here I have minus. Here and when without differentiation, I have to have plus minus. But when I differentiate, I get another minus. So there should be minus and plus. So I see that, and I know that U classical equals to 3/2 and theta. It's a well-known formula from school and so on. I see that U classical is lower than the U of Fermi gas, but the internal energy of bosons gas is lower than classical gas. Why this happens? Why the bosons have lower internal energy than the fermion gas? It's quite easy to explain this fact. We can compute the internal energy using the occupation numbers and energies of one particle state. The numbers n sub n are defined by the Bose-Einstein statistics. So I have epsilon L minus 1 divided by theta minus plus 1. And n sub L for fermions is higher than for classical Bose gas, for classical gas, Maxwell-Boltzmann gas, and higher, lower, because here fermions I have plus 1, so I divide by bigger number, occupation number is smaller, and here I have, and for bosons, the occupation numbers are higher than in the classical case. This means that in Bose gas, the number of particles with small value of energy is higher, so the energy is lower. For fermions, the number of particles with higher energy is bigger than its in case of fermions, the number of particles with lower energies is smaller than this classical case. So the fermions has to occupy the states with higher energy. And in this case, we have more particles on states with high energy. So internal energy of fermions is high. When the temperature increases, okay, the particles, the gas more and more resembles classical gas. In this case, the extra particles of higher energy fermions will decrease their energy, and for energy of boson particles has to increase to be closer to the classical statistics. That's why the heat capacity of bosons is higher than the classical case of fermions and lower the classical case. And we have several minutes to ask very important questions. Very important question. What will happen if the gas is not rarefied? So, the condition which we defined as follows. Is no longer valid. Yes. Okay, I will write here. Is no longer valid. That is here I mean something like this. Is it possible? Is this possible or not? My statement is that dense quantum gas has special properties that are very different from classical gas. And these gases are called degenerate. And in next two lectures, we will consider the properties of degenerate boson gases and Fermi gases. So, so the lecture is finished. Do you have questions?
Почему, еще раз, вот у нас, если NL для фермионов, оно меньше, чем NL для бозонов, то энергия, наоборот, у фермионов
Okay. Okay. Why the smaller occupation numbers for fermions implies higher energy? Okay, it's a good question. Let us assume that the number of particles in gas is constant. In this case, we have to distribute these particles, the n particles, in the quantum one particle states. We know that the system takes that the particle prefer to take the states with low energy. So we have, let's say, states. Okay, let's say states, and let's say states for bosons.
Ну все понятно. В общем, меньше электронов на более заполненных оболочках. Ой, в смысле, на нижних уровнях, поэтому больше на верхних.
Okay, yeah. So when we deal with fermions, they can't occupy many low energy states. They have to grow to higher energy. That's why we have higher average energy for the fermions.